Hey man,
Hello.
how are y'all?
It's raining.
I can see that, yeah.
Yeah.
Are you gonna drink that? Oh my gosh, what were the chances of... Dude, like, I know it was raining and all, but what were the chances of all that water just falling on you all at... Like, I don't even... How could that happen? What were the chances of that?
Greetings and salutations, Beau Maths fans around the world. Welcome back to another episode from yours truly. And today we're going to be continuing proportion stuff. We see proportions show up in a really wide variety of ways. We've talked about how they can be used to represent what portion represents a total and how this connects with fractions. We've used it with fraction multiplication to apply proportions to different group sizes. We've used standardized proportions in the form of percents and saw how we could connect that with all the math we've been learning. And today we're going to continue this proportions train by talking about how proportions can be used to describe chance, basically how likely or unlikely an event actually is. And this is what we call probability.
Proportions of chance.
So if we think about probabilities, or these proportions of chance, how likely or unlikely an event is, in terms of percentage, right, standardized proportions, we would probably expect that 0% would mean that the event is impossible to happen, right? Because if there's a 0% chance of happening, well, then that means there is literally no chance of it happening, right? That's like the lowest possible chance. It just doesn't occur. And what would the highest possible chance be? What would 100% likelihood look like? Well, that would be, it's guaranteed, right? There's no room for, oh, maybe it's not going to happen. If it's 100% going to happen, it's guaranteed to happen. So 100% probability or chance is guaranteed. So, for example, there's a 0% chance that you aren't subscribed to Beau Maths, and there's a 100% chance you're going to like this video, right? If we convert these into proportions or fractions, we know 0% converted into something without a percent would just be 0, right? Because 0 over 100 is 0, and 100% is 1, since 100 over 100 is 1. So if we're thinking about proportions, that means it ranges between 0 and 1, from impossible to guaranteed. And so unlike percentages, which can sometimes go over 100%, when we're looking at them in the context of chance, in the context of probabilities, we're always going to be stuck between 0 and 1, because it doesn't really make much sense to have something that's even more than guaranteed or even less than impossible. And because we're using percent, we can already get a good idea for what probabilities are likely and what probabilities are unlikely. So 90% probability would be pretty likely, right? Whereas a 10% probability would be pretty unlikely, right? Not impossible, there's still a chance, right? A 10% chance that whatever you're measuring can happen. And there's one idea that I did very briefly talk about in the last video regarding the percentage tricks, and that was the idea of a complement. And I said, oh, it's used in more complex math, so we're not going to worry about it. Well, I lied. We're actually going to be using it today. It's not that complicated. So let's talk about the complement.
Complements.
So we can think about the complement of a percent as what completes it to 100. So for example, the complement of 40%, well, what makes 40% into 100%? By adding 60%, right? Is 60%, right? And this is since 40% plus 60% is 100%, right? So what would the complement of 35 be? What number can you add to 35 to make it 100? That would be 65. So the complement is going to be 65%. And since we're thinking about probabilities as percents, we can also kind of say this is the same thing as the complement of a probability as well. So if the probability is 40%, the complement is 60%. If the probability is 35%, the complement is 65%. But then that also means if we're viewing a probability as maybe like a proportion in here, so what would the complement of 3/5 be? So 3/5 could be converted into a percent, but this is just some probability, right? 3/5 is between 0 and 1. It's a proper fraction. Well, what can I add to 3/5 to make it into 1? Well, 1 would be 5/5, right? So if we add 2/5 to 3/5, right, with that common denominator, we'd be getting 5 over 5, which would be 1, right? So the complement of 3/5 would be 2/5, since 3/5 plus 2/5 equals 1. So remember, 1 is 100%, so basically we can also think about what completes it to 1, not just to 100%. So it kind of depends on the perspective we're taking, but it's the same idea, right? We could convert this into 60% and then this into 40% and we'd get it. So what's the point with me talking about the complement here? So suppose there is a 90% chance I break my back playing as a guest football player. So suppose there's a 90% chance I break my back playing as a guest football player. So what's the complement to 90%? Well, that's going to be 10%, right? Because 90 plus 10 is 100. But what does that 10% actually represent? If 90% is the chance I break my back, what's the 10% represent? Well, that would be the chance that I don't break my back, right? So this is a really important idea. So basically the complement gives us the chance of the opposite event happening, right? If there's a 70% chance that something happens, then there's a 30% chance that it doesn't happen. So that right there is the purpose of talking about the complement. Let's actually talk specifically about how one goes about finding the probability. I mean, how would someone necessarily know that there's a 90% chance that I break my back or something like that? I'm just pulling these numbers out of nowhere right now.
Calculating probability.
So recall, the probability is the likelihood of an event occurring. And the way you calculate it is it's the number of desired outcomes divided by the possible outcomes. So if you're looking at the likelihood of something happening, you take the amount of times that it can happen and divide it by the amount of possible outcomes total. So let's just start with a simple example. So what's the probability of flipping a coin and getting heads? So if you take a coin, there's the tail side and there's the head side of the coin. And so when you flip it, there's basically one possible way to get a heads, right? There's only one heads, and there are two different outcomes, right? There's the head side and there's the tail side. So our probability then would be 1 out of 2, which we could convert into a percent if we wanted to be 50%. So it's a 50% chance that we get a heads. So not super likely, not super unlikely. And in fact, since it's 50%, that means the complement, or the chance that we get a tails, right? That would be the complement of this event, is also 50%. So that means there's the same likelihood of getting heads as it is tails. That's what we would call a 50-50 chance. All right, so let's flip it. Tails. So I did not succeed in getting a heads here, but hey, I had an equal chance of getting a heads as I did a tails. Let's try a little bit more of a complicated example. So here I have a 100-sided dice, right? It goes from 1 all the way up to 100. And I want to know, what's the probability of rolling this and getting a multiple of 10? How many outcomes satisfy this idea of getting a multiple of 10? Well, what are the multiples of 10? There's 10, 20, 30, 40, all the way up to 90 and then 100, right? So there are 10 different multiples of 10 between 1 and 100. So that means 10 are the number of our desired outcomes. That's how many numbers on this dice actually fit this property here. And then we divide by the total possible outcomes. Well, there's 100 different numbers this could land on, right? So we're going to divide by 100. But 10 divided by 100, that is the same as 1 over 10, which is 0.1, which is 10%. So we could say there's a 1 in 10 chance of this happening, or there's a 10% chance of this happening. But it's not super likely that we're necessarily going to get a multiple of 10, but let's roll it and find out. And because my table's slanted, this just rolls all over the place because it's kind of like a ball, so I'll just let it kind of settle between my fingers here. All right, and we landed on 33, which is not a multiple of 10, which, I mean, not a multiple of 10, that's the complement of getting a multiple of 10, and the complement of 10% is 90%, so it was much more likely that we didn't land on a multiple of 10, and this result reflected that. Okay, so hopefully you kind of have a decent idea for how to calculate probability. It's honestly pretty much the exact same thing as what we did when it came to calculating the proportion in general, right? It was the number of things that satisfied a certain property divided by the amount of things in total, right? For example, we have 10 dentists, 9 of them like a toothpaste, so the proportion of them who like the toothpaste was 9 out of 10. We're doing the exact same thing here now, except we're adding kind of a spin on the perspective and saying it's the chance. So in that situation, we would say that if we just picked a dentist from that group at random, the chance of one of them liking the toothpaste would be 9 out of 10 or 90%. Right? So we're just kind of adding a new perspective on an old idea.
Applying probabilities.
So just like proportions, we can apply probabilities to groups of different sizes. So for example, we could say something like, how many times would you expect to get heads if you flip a coin 70 times? So we know from a previous example we just did that the probability of getting heads is 1 out of 2, or 50%, right? Because there's only one way of it happening out of 2 different possible outcomes. And now what we're going to do is we're going to apply this probability, or apply this proportion, to this 70 times that we actually flipped the coin. And how did we apply proportion? That was through fraction multiplication, right? That's why all this stuff has come after the fraction multiplication video, because they're all applications of fraction multiplication. So if we do 1/2 and we multiply it by 70, all right, so to multiply these, it's numerator times numerator, denominator times denominator, so we make this 70 out of 1, and we're going to get 70 over 2, and 70 divided by 2 is 35. So we would expect to get 35 heads if we flip the coin 70 times. And we could do a similar question, but for the 100-sided die. So how many times would you expect to roll a multiple of 10 if you roll the 100-sided die 590 times? So that's a lot of rules, but thankfully all we have to do is take the probability of getting a multiple of 10, which was 1 out of 10, and then multiply it, or apply that proportion to the group size, which is how many times we're actually rolling the dice, which is 590. So then multiplying this, we get 590 over 10. Dividing by 10 just takes our decimal, slides it over 1. So we would expect to basically get 59 of these rolls, resulting in a multiple of 10. So the way you apply probabilities is you multiply the number of trials. So that's how many times you basically try the event, how many times you flip the coin, or how many times you roll the dice. So you multiply the number of trials by the probability, and that gives you your expected value. So what would you expect to get? How many of those events would you expect to actually result in a heads, or how many would you expect to result in getting a multiple of 10? All right, now this is the expected value. This is what you would expect to get, but life is random, right? There is a chance, a small chance, but there is a chance that I could flip this coin 70 times and every single time get heads, or every single time get tails, or maybe 60 of those times get heads and 10 of those times get tails. Or I could roll the die 590 times and every single time maybe I land on a 1. Or I could roll the die 3 billion times and every single time land on an even number, right? So just because these are the expected values doesn't necessarily mean that's what we get in reality. And so this introduces an idea called relative frequency.
Relative frequency.
So the way we calculated the probability was it was the number of desired outcomes, or the number of ways the event could happen, and we divided it by the possible outcomes. Right, so the probability of heads, that was one possible way to get heads and 2 different possibilities with flipping the coin. But to contrast this, relative frequency, this is a little bit more experimental. So we take how many times we observed the desired outcome, and we divide it by how many trials we did. So what does this mean? Well, up here, to figure out how many times we would expect to roll a multiple of 10, if we rolled the dice 590 times, all we did is we took what our probability was and we multiplied it by 590. We didn't actually have to roll the die 590 times. But to get the relative frequency, we actually have to roll the die 590 times. So here we would roll the die 590 times, and that would give us our trials, right? Because we did 590 different trials. That's how many times we actually rolled the die. And then let's say of those, we saw only 30 resulted in a multiple of 10. And that is how many times we observed our desired outcome, right? We wanted a multiple of 10 and we observed it 30 times. So that means our relative frequency in this situation would be 30 out of 590, which if we put that into our calculator, we get 0.051. I'm just going to round it to a few decimals there. So we could convert this into a percent, multiplying by 100%, which would give us 5.1%. So that's fairly different than the 10% that we expected the probability to be. So does that mean the probability is wrong? No, what it means is that the probability is like an ideal amount. It's the amount that we would expect to happen, but it's not necessarily the amount we get in reality. So this models the situation. It gives us a good idea for what should happen, but what does happen is often different, right, with the relative frequency because it's random, right? Chance doesn't necessarily have as much of a structure as probability would maybe suggest it does. So, is there a way to somehow bridge the gap between relative frequency and probability? And the answer is yes, and this is called the law of large numbers.
The law of large numbers.
So what this is saying is that if you do a certain amount of trials, right? Let's say you flip a coin 30 times or something like that, right? That's going to have a relative frequency to it, where you'd be able to calculate how many times we actually got a heads divided by the 30 trials that we did, the 30 times we flipped the coin, and we would get our relative frequency. And that might be 50%, but it might not be. It would be probably a little bit off. But what the law of large numbers says is that the more we do these trials, right? If we do 100 trials or a million trials or a trillion trials, the more trials we do, the closer our relative frequency will start to look like the probability. And so that's why it's the law of large numbers. So if you have a large amount of trials, that relative frequency is going to be really close to your probability. And this kind of gives us another perspective on which we can think about the probabilities being like this ideal situation or this ideal outcome and not like super realistic. Because what we can think of this as is basically if we were to do infinite trials, then our relative frequency would become our probability. Be guaranteed to be the probability. So this is a really interesting idea where essentially the relative frequency is like it's a realistic thing. It's something that it's a lot more random because chance is random, right? Flipping a coin is random, rolling a dice is random. But it's as though the bigger the number we get, it's this randomness, it starts kind of not mattering as much. It starts getting confined to the structure of what this probability is actually saying. And that's a really, really cool idea because you have something that's completely random still ending up actually kind of converging into some sort of structure, namely what the probability is. And this is a really common idea in mathematics, a really fascinating idea in mathematics, where you have something that kind of roughly approximates what's going on, right? Because I could do the relative frequency. I could do 30 trials and I could get 7 different relative frequencies, right? Because each time I do those 30 trials, I get a different amount of desired outcomes. So the relative frequency isn't fixed for a certain amount of times I roll the die or for a certain amount of times I flip the coin. If I flip the coin 10 times, I could get 9 heads or I could get 7 heads, I could get 4 heads, right? So the relative frequency keeps on changing because, well, it's random, right? But what this is saying is that the more and more trials I do, the relative frequency kind of starts losing its roughness. It starts losing its randomness and it starts converging. It starts kind of becoming this probability. That's the power of these really big numbers. That's the power of infinity. It starts removing this roughness. It starts removing this randomness from the situation and kind of settling it in on some sort of structure.
Concluding thoughts.
All right, so I hope you found today useful. We introduced the idea of probabilities, these proportions of chance. It's yet another perspective we have on proportions, yet another perspective we have on fractions and what we can do with fractions, fraction multiplication. And we talked about some really cool ideas regarding relative frequency, kind of like what we observe in reality versus this ideal of probability, and how these really big numbers and infinity actually can kind of bridge the gap between what we see in reality and what this ideal actually is. So I hope you found that video useful. This was one of the more interesting ones I've done in a while, in my opinion. But in any case, you have a good one, you stay groovy, and I'll see you in that next video.
I mean, like, what are the chances? Like, 1 in 10, 1 in 100, 1 in 1,000, a million, a billion? I mean, if we're assuming like the average raindrop has a diameter of like 1 millimeter, like that had to have been at least like what, like 20, 25 centimeters worth of rain pouring on you all at once. So I mean, like for all of it to be concentrated in that specific of an area, that I think the chances would probably be like somewhere in the realm of like, 1 in 652,000 ish. Like, does that seem reasonable to you, or like am I a little
Beau Maths.